Hi and welcome back. Before we start this video, I was playing around with our scales generation and I actually achieved a look I like better because it features some more worn out appearance. And if you want to achieve the same, well, first thing I did is I went to the generate scales and I changed the seed. I made it dependent on our primitive ID. So if I show you, so we have this just like we did in the previous video. And I just added this primitive ID to the seed instead of adding it to our deformation because here it will be easier to control. And in the deformation itself, if we dive into it, first of all, I changed it to sparse convolution noise and I made it fit because I thought that sometimes I actually do want it to go the opposite direction, so I didn't clamp it. And here I put -1. You can also control it, for example, put -0.3, so not always it will go in the direction of our normal. And as you can see, our stuff exploded a bit, so make sure to play around with it a bit more. So let me see. So yeah, as you can see, it starts expanding, as well as you can play around with these values and see what you like best. So maybe I will actually decrease this one. Yeah, it looks nice. So yeah. So that is for this fit range. Another thing I changed is I realized that we are taking a vector and then we are treating it as a float, which is incorrect. That is why after our second multiply, I put a vector to float. Because previously we were just connecting it directly to float to vector, and that is incorrect because we haven't actually made a float out of it. So make sure to have this. And I also plugged y because I realized that we need it since our normals feature values in both x and y. So I made it half of the value because if it's a full one, I find it a bit too severe. So I can demonstrate you that. So yeah, I find it's a bit much, but maybe that's what you want to make them look very different, but I still want them to look kind of uniform. So I keep it half of the value and just a tiny value to make some offset in z-axis, and everything else stays the same. So we just add everything to our position. So yeah, that stayed the same. And I made the amplitude 0.6. And yeah, the offsets, I just copied our random seed. I made a random out of it and I just multiplied by 10. And in others, I just add different numbers or subtract different numbers and multiply by different value. And here I have division and multiplication. So that's pretty much it. And I have this result, which I like much more. And here I just copied it. And here we already will have different seeds because we have different primitive IDs. So I didn't have to go and edit anything. Oh, actually, one thing I did edit, I think in this one, yeah, I lowered the amplitude, so not all of them look the same. I guess you can also make a random value here based on the seed. So some of them are deformed more than others. So yeah, I think that's also a nice addition. But yeah, that's what I did. So that's what we have after we transform everything. So I'll go up and up, up. I haven't changed anything here, I think. And it's still, oh yeah, because I picked the view. So yeah, this is our wall. And you can see right away that our scales look much less uniform than they used to. And that is exactly what we want. So yeah, I'll go up and generate everything. So here we are. And we have all of our scales. Yes, it looks brilliant. And I see that actually, oh no. Am I glitching or they're the same? Because I see this indent, I see absolutely the same indent in here, so, this one's they look a bit different, so let me check what's happening. Okay, so, now it seems alright. So I'm not sure if I was just glitching or it was actually true, but, I just made the order a bit different. So in scales, I actually made the seed in our loop for just both scales. And in the seed, I put the body seed and the stamp. And I copied it and I put it into our seed here instead of the body seed because our body seed is already in this one. And yeah, I call this one seed scales pattern. So this one is seed scales pattern. So I'm not sure if this fixed it, whether this was an issue, but I just made this order and I decided not to be lazy and actually made the order properly, because that's how I usually would do it. Because, yeah, seats can be a bit confusing, so you have to always keep track of them, and this way you can always see what's going on, and I think it's easier. So, yeah, that's fixed now. And I will go up and up and up. So yeah, that's where we left off. And before we continue, I actually want to show you something, because now we will move on to generating geometry for roofs, so roof shingles, as well as the sides of our roofs. And yeah, before we do that, I will just quickly show you something. When we were generating scales and wood for our walls, we were having different parts. So let's imagine we had like a part like this, and a part like this. Yeah, sometimes part like this. And all of these parts we were taking, and we were generating geometry exclusively for those parts. So we would take every part and we would populate it with like wood or scales. And those ones, they were unique. Thus, generated every time. Yes, we had an algorithm, and this algorithm was repeated as many times as we have wall pieces. So the more wall pieces you have, longer it will take. However, with roofs, I want to show you a different approach. With roofs, we have just pieces like this. And what we're going to do is we're going to have a huge, let's call it canvas. And we're going to measure each of those. So this is X and Y. And we're going to randomly cut out the same dimensions. And to make sure that all of our roofs still look unique, we would cut out different ones. So if this is X2 and Y2, so this is X1, U1, then the other one would be somewhere here, for example. And this technique is closely intertwined with our UV space. If you remember when we had UV space, this is kind of similar, because in a way we're also choosing like a random place, and we're also accounting for the dimensions in world space, because what we're going to do instead of UV space, we're going to translate from world space into our canvas space, which is a very similar technique. And this way, no matter how many roof pieces we have, the generation time will stay relatively same, because we're going to generate this canvas only once. So that is the idea. So let's implement it inside of Houdini. So that is where we left off in the previous part, and now we will dive into our roof modules. And we're going to grab our extensions, and yeah, let me unpin the view. So that is our roofs. So what we want to do first is we want to isolate the roofs from the sides, because they will have different patterns. So roof and just say that side is equals to 1, and yeah, delete it. Beautiful. So now let's create a null. Collapse it into subnet, which we will call roof. Geo stands for geometry, and generate. And let's color it. Yes, and dive into it. Call it in, as we usually do. And the first thing we want to do is generate the canvas. So let's grab another null, collapse it into a subnet, and we will call it roof canvas. So we don't need a null anymore. And in here, we're going to start with a grid. We need to make sure that it's big enough. It's in XY plane, yes. And we do not want any rows or columns. And 10 by 10, I think, is more than enough. And another thing is that, as you can see, we have our normals pointing in the opposite direction, and we need to fix that. Otherwise, our extrude not going to work the way we expect it to. So rotate it. Yes, nice. And now we can generate the scales. And the way we're going to do it is, you might already guess, is just by copying what we already did before. So I'm going to body modules, main body loop. Yes, all of that beautiful stuff. We just copy our scale subnet. Let me see if I copied it. Yes, Go up and up. Don't generate anything, please. And up again. Don't generate. Oh, whoa, 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 whoa. Pressed something there. So roof modules and roof canvas, and in here, plug it and it should work. Let's see. And ta-da! As our generator was constructed correctly, it would work for any size. So let's dive into and see what's happening. So yeah, we have our tile. Yeah, then one thing that we have to fix is definitely our tile grid. It also has to be 10 by 10. 10 by 10. And expand should work now. Yes. So now let's generate again. It should fix our borders because as you saw, some funky stuff was going on there. So let's see. Yes, and it fixed our borders as well. So beautiful, beautiful, beautiful stuff. Oh yeah, I didn't mean to go out. So I don't need to generate anything. So the thing I want to do now is I want to modify the shape. And the way I'm going to do it is I'm going to go inside of generate the scale. And I'm just going to delete both clips. And now our generation will be maybe a bit too brutal. So let me make it maybe like this. So let's go up. Don't generate anything because I want to do absolutely the same in here. I will delete both clips and in deformation also a bit smaller. And as you can see, we have our shingles. So let's go up. So that is our canvas. So let's go up, and that's pretty much it for the canvas. Very easy, right? So let's color it. So now we can start applying this canvas to our pieces. And the first thing we would want to do is we would generate proper normals. So for that, post compute normals. So, and unique points. Yes. Perfect, because previously we had these normals, which are correct for the modules placement, but not for this case. And also, one thing we want to do is we want to pick it. Why do we want to pick it? Because our canvas has a thickness, which we haven't accounted before. Because in here, our roofs are infinitely thin, so they do not actually take into account the thickness of anything. And that is why we want to pick it for the same value as we extruded our scales, or shingles in this case. We don't want to recompute, and this scale was 0.05. So that's what you should have. Beautiful. And now we can just start generating. So let's create a for each subnet. And we'll plug this and that, and we will call it, let's call it canvas placement. Yes. And we just want to run it for each primitive, and we're going to rename it to canvas place. Canvas place, yes. We'll copy that because we would need it for our seed, and let's color it as well and dive into it. So in here, yeah, we already have our nice, beautiful piece. And first things first, let's not be lazy like last time. Let's create the seeds everywhere so it's easy to track them. And yeah, edit parameter interface, usual stuff. We're going to call it seed canvas roof placement. Why roof? Because we're going to have another canvas for sides. So here it's just seed. And we're going to put, it's a stamp of our long name. And yeah, that's it. Beautiful. And now that I'm thinking about the seeds with our roof canvas are not going to work now anymore because we changed the location of those nodes. So we're just going to connect them to the global seed. So I'm going to go back to the roof canvas, back to the scales, back to this one. And in here, yeah, we still want to keep the stamp, but we want to, let me grab a transform node so I can paste relative reference. We just want to paste the global seed here. So, because we do not have this seed anymore. So, yes, that should work. Apply, and now it should, unfortunately, regenerate everything, but we just wait. So, oops, yeah, that is our shingles. So I'll delete the transform node. Yes, everything is in order. So let's go up and up again. And that is in our canvas placement. So now as we have the seed plugged as well, we might also connect it to the global seed. Why not? So paste relative reference and plus. And now our challenge is to put every piece into the center of the grid and make it rotated along the z-axis. We already dealt with having angles, but in this case, our piece is rotated in 2 axes instead of 1, like we had with our walls. And those axes are, we have rotation along y-axis, as well as we have rotations in z and x. So we have to deal with those, and we're going to do it step by step. So the first thing that we want to do is we want to make it aligned along y-axis, and then we're going to deal with the y rotation. So to do that, let's grab a wrangle node, and we will call it rotation x and z. We're going to color it right away, and we're going to make it run only once because we need to calculate only one value, which we're going to feed to a transform node. So in here, let's make it bigger. Yes. And in here, the way we're going to identify our angle is, of course, based on its normal. So we'll grab the normal. So it's a point, 0 index input, normal, and any point, because all of them have the same normals. We're going to normalize it, though I think it's probably already normalized, but just to make sure. And we would need 2 floats, which are dot product and the angle. And the first thing we're going to do is we're going to look whether, so I'm going to make it smaller here. So yeah, like this, so we can see the shape as well. So the first question we're going to ask is whether normal x value, whether it exists at all, because in our case, we cannot have both x and z rotation. It's either one or the other. That is why we have to check. So first of all, we do not care whether it's plus or negative, and we want to just know whether it exists. So we're going to rent it, and we're going to ask, does it exist? So if we have some rotation in x, and in this case, we do not, we have only z and y. However, I'm still going to write this case as well. So first things first, we want to calculate our dot product. So this is a dot of our normal and the x-axis, and the angle is degrees out of our cosinus of our dot. However, we would need to write a couple of constraints. We need to see whether the normal x is positive or negative. And based on those, we will modify our angle. So if it is positive, we want to subtract the angle from 360. And if it is not, we want to subtract it from 180. So that is for the x. And I'm going to comment, check whether the normal has value in x. And now, else. Check whether the normal has value in z. So, if we do not have anything in x, that means we have something in z. And that's very similar, so we also want to do the same steps. Instead of x, we're going to check for z-axis in here. And here we also have to check whether it is positive or negative. If it's positive, we don't want to modify it, but if it is negative, so normal dot z, then our angle is added to 180. And then we just say that our angle is angle. And currently we're not saying where exactly we have to rotate it, in z or in x, but we will write it in the transform node itself. So apply intercept. And now I will bring a transform node, which we'll call rotate x and z. And in here, in translate, we're going to write that look at the detail of op input path, yes, of our angle node, and look at the angle value and apply it, so multiply, so apply it only if we have any rotation in Z. Of input path point number 0, normal, and second. So we want to check whether we have any value in Z. So if it is not equal to 0, then we're going to get a 1. But if it is a 0, we're going to get a 0 value here. So I'm going to round it as well. And we're going to copy it because we're going to have a very similar thing in our Z-axis. So apply and accept. And in here, same thing, but here we should check for X. And currently it is rotating around the origin of the grid. That is why it just disappeared. So make sure to assign correct pivots to the center of our shape. And F. And oh yeah, I applied it in translation. Oopsie doopsie. So let me apply it for the rotation. So delete. And here as well. And delete. So as you can see, we aligned it along y-axis. So if I go up and I applied for everything, that is what happening. So you can see we had this, and now all of them rotated to be aligned along y-axis. So now the question becomes that some of them actually already pointing in positive z, but many of them actually don't. So the next step is easier than the previous one. We again want to grab a wrangle node. And now we want to calculate the rotation in y. So rotation y. And again, we want it for detail. Bring it bigger. And here, we're just going to do it faster. So it says that float angle is degrees from our cosinus from dot of normalized version of our normal. Maybe we should get it from point so we can use this, but no, I want to have a detail. So let's grab a vector normal. So that is point 0 index input and 0. So let's replace this with normal. And in here we want to grab the z-axis because that is the axis we wanted to align to. And now we just say that if normal.x is a positive one, we want to invert our angle. So our angle is a minus angle. And I would just say that angle is, well, angle. So apply and accept, and we're just gonna have a new transform. Actually, I'm gonna copy this one. And we do not need X or Z anymore, because we're gonna use now, well, I should have copied. We're gonna use now y-axis. So, and in here, we do not want any of this, we just want the angle. So apply and accept. And yeah, sorry, there was something weird going on, but as you can see, as soon as it updated, all of our pieces are pointing correctly in z-axis. So let's rename it to rotate in y. I'm going to color this one as well. And now we can just put it on the origin of our grid with a match size node. So match size. And we're going to just add a point. And yeah, uncheck scale, and ta-da! We have our piece nicely placed and oriented in the world space. That's beautiful, because now we have to grab our canvas, which is right over here. Yeah. So let's create a null. Let's call it in canvas, because now we are ready to cut out a piece from it, which we will be dealing in the next video. So thank you for watching, and see you soon.